Hello, this is the data flow diagrams presentation and it was created by Kadous, Bittencourt, and Josué Ruiz. Now, what is a data flow diagram? A data flow diagram will help you completely map out the system in relation to data. It will help you completely describe all the data that enters and leaves a system, the checkpoints it may go through, and how data is transformed from one state to another, and where data is stored. It will not tell you how data is stored. It will not tell you how functions work or how they call upon another, and it will not tell you how algorithms in the system work. The purpose of a data flow diagram is to show how data flows through a system. Now here we have a very simple example of a one-class program. And on the right, we've listed out the notations commonly used in data flow diagrams. We have interactors represented by a square box, flows represented by arrows, processors represented by round rectangles or sometimes circles, storage represented by two lines, and trust boundaries represented by dotted lines. In this example, we have a user who sends data as commands to a UI processor that then sends plain text data to a set processor, which then sends hash data to be stored in the password class. It can then be retrieved using the get processor or function, and eventually that is then sent back to the interactor of user. It's a very simple example of how data flows through a program. Here we'll explain the 5 components of a data flow diagram, or the notations which were shown in the previous slide. The interactors are agents that exist outside the system. They provide and consume input. Common interactors are users, networks, and programs. So basically anything that interacts with the system to provide input or receive output is an interactor. The flows represent the movement of data from one location to another. They must always start and stop from an interactor, processing node, or data storage. The processors are location in the program where data is transformed or checks are performed. These are often functions, though the functionality will not be represented in the data flow diagram. Storage represents the data at rest. These may be variables, files, or other objects. And the trust boundaries represent different levels of security or trust, maybe a program, a class, or the operating system. Often, for trust boundaries, you can go multiple levels deep into a program when making a data flow diagram.
So just to give an example of how data flow works, we're going to show you a demonstration. We have a class called room, which sends a variable through the function setName to a class called name. And later, if we want to retrieve that variable, the class name has a function called getName, which sends the information back to the room class. The advantages of using DFDs are: it's widely used in structure requirement analysis phase. It represents structure of a system visually and naturally. It saves developers time trying to understand code. It's simple and easy to understand. It helps track the origin of data and how it passes through the system. And finally, it shows how data is verified or transformed through various steps and where it is stored.
Below we listed some of the disadvantages of using DFDs. DFDs are not suitable for user-designer interaction. DFDs cannot represent all aspects of a software project. Sometimes DFDs are taken for granted from BAs. Not all functions are listed in a DFD. Details of the data representations are not described. The algorithm or how the program works is not represented. And here are some of our recommendations on DFDs. DFDs are better to check for completeness, to find missing requirements, or for re-engineering projects. Instead of building one big and complex DFD, build many starting from the big picture, often called context diagram, and down as many levels as needed. Finally, here are the references we used in order to build this presentation. Thanks for watching.